Alright guys, welcome to another simple engineering snippet. Okay, this video is going to be a little bit different in that we are going to be showing how we can use the method of characteristics for waterhammer or hydraulic transients in a pipeline. So a little bit different type of video, but I hope you find it useful. Okay, so the main reference for this is going to be an excellent book, Fluid Transients and Systems, by Professors Wiley, Streeter with Sewell. And this is going to be the first snippet in a series because it's going to be quite long. In this video, we're going to be showing how we can lay out the method of characteristics to analyze a hydraulic transient in a single pipeline. And that's to set the stage for some further investigations. In subsequent videos, I'm going to be doing some grid convergence tests, adding additional boundary conditions, and so forth and so on. So I hope you find this series useful. Okay, so let's start governing partial differential equations, conservation of momentum, and conservation of mass. And these are already simplified a bit in that we've ignored the convective terms based upon the speed of the wave speed. The celerity is typically much greater than the fluid velocities in a pipe. Note that we do have the celerity, and this accounts for the slight compressibility of the liquid and how it impacts the pipe. So these are partial differential equations that depend upon, in this case, the spatial variable x and time. And to go ahead and define things is that you'll notice that there is no gravity term here. That's because we're using piezometric head, which is the static pressure head plus the elevation. The other terms are hopefully self-explanatory. Okay, so even without the method of characteristics, we can use finite difference schemes and other schemes to compute this solution on this on an XT grid. And we're going to be doing that. Well, I'm not going to be doing that. We're going to be using XT grid, but we're going to go ahead and take a rather typical discretization where the center node is ij, and then I minus 1 is to the left, I plus 1 is to the right, and j changes as shown. And before we dive into a solution, let's go over a little bit of how the point red, the node in red, what does it depend upon? Well, there's a domain of dependence, which is set by the characteristics, which is going to be key for the method of characteristics. And the solution to this point in red, which is at I, j plus 1, depends completely on this shaded area, and oftentimes that's referred to as the domain of dependence. And when you achieve this, that is not only stable, which is always good, but it's also your most accurate solution. This will correspond to a Courant number equal to 1. And I'm not going to dive into the mathematics of this, but the Courant number is equal to the fluid velocity times your time step divided by your spatial grid discretization delta x. When that's equal to 1, that is stable and your most accurate solution. Conversely, if our delta t is smaller and our Courant number is less than 1, well, that's stable, so that's good, but it's less accurate. Why is it less accurate? As well, we've included in the computational domain information at the tips out here that really this node in red, I, j plus 1, does not depend upon. So that's introducing error. So while your solution is stable, it's not going to be as accurate. If we go to the other extreme where delta t is too large, then now our computational domain does not include everything that we need. So it's missing the information out here at the endpoints, and in that case, it's unstable. It's a little bit annoying to me when people start talking about the accuracy of their unstable scheme. It's unstable. Okay, so conservation of momentum, conservation of mass, we've done nothing yet for the method of characteristics. These are just partial differential equations, but the method of characteristics is going to allow us to convert these into ordinary differential equations, which are much simpler to solve. Okay, so let's step through how we're going to do this. I am going to be going very quick. I recommend you purchase the Wiley and Streeter text. It's excellent. And what I'm doing is pretty much laid out and follows along with how they do it in that textbook. Okay, so I'm going to skip the details, but typically they take these governing equations and you add in a multiplier and use the definition of the total derivative, and you're able to come up with two pairs of equations. So the first pair is an ordinary differential equation right now depending upon time, and a second pair. Now, these can't be used everywhere. There are restrictions in that these are valid only along the lines of characteristics, hence the name method of characteristics. Okay, so there's a C plus characteristic, which we're going to be drawing on here in a second in the xt plane, and a C minus characteristic. So what do I mean? Well, here they are. So we have the same node in red that we're hoping to find a solution. We're going to be marching through time, where we know everything at time level j when we're trying to solve for the points at j plus 1. And the first pair of equations is valid along the C plus characteristic, and the second set of equations, pair of equations, is valid along the C minus characteristic. So now we need to integrate these along these characteristics. We have two unknowns, head, piezometric head, and flow, and two equations that's going to allow us to solve for that. Okay, now you'll notice this looks pretty familiar in that the way we've laid out our characteristics corresponds exactly to our most stable and accurate solution. So that is the good part of a method of characteristics, is that you stick to this grid. You are going to obtain, from in terms of finite differencing numerical scheme, the most accurate solution. You're not going to be introducing anything that's going to cause instability and or additional error by having your Courant number less than 1. There's some downsides to this as well, which we'll be discussing a little bit in this video and subsequent videos. Okay, so let's do this for the C plus characteristic. This pair of equations shown is valid along the C plus characteristic. And let's call the first one equation A, the second equation B. So we're going to be integrating these pairs of equations from point I minus 1j up to the point I j plus 1. Okay, well, the first thing I'm going to do is take the equation A and multiply it by the time step dt. And this is the result. So now I've gotten rid of the differentials with respect to time, but I am still left with a dt. But the second equation, I look at it and I see that, well, I can manipulate that, and I see that the celerity times dt, which I have in this last term here, is equal to dx. And so I can replace that with dx. Again, that is no longer a variable. That is my grid size in the x direction. Oftentimes you'll see that denoted as delta x. Okay, so this is my equation. Right now I'm not done any finite differencing schemes or anything like that. So we are going to integrate it from the point, again, I minus 1j to I j plus 1. So noting that, I'm going to take the integrals of the three terms separately. Well, the first two terms are straightforward. That's just calculus. And so that falls right out. There's no approximation there. So we're only left with this last term. And that's a little bit more troublesome. Why is it a little bit more troublesome? As well, we don't know the volumetric flow rate as a function of x. Now, we can make different approximations and assumptions and say for a really small step size x, delta x, it's approximately a constant. But there are some little bit more elaborate schemes that Professor Wiley and Streeter came up with. And so let's attack that term right now. And what we're going to use, the first tool we're going to use is integration by parts. The integral of u dv is equal to uv minus the integral of v du, where u in this case is q squared and dv is dx. And so I'm going to apply integration by x. This term right after the equal sign, that's actually two terms that needs to be evaluated at the points xi and xi minus 1. And so when we do that, again, so far, all we've done is calculus, but we're not done yet in that we still have the last term, which is still troublesome because we still don't know q as a function of x. So this is where we are going to utilize a numerical scheme. We're going to numerically integrate this term. And so starting out at that point, what are we going to use? We're going to use the trapezoid rule. And it's globally, it's second order accurate. Locally, it's third order accurate. But globally, it's a second order accurate scheme. And second order accuracy is pretty darn good. And so here it is. The product of the brackets and the parentheses, that is the area of a trapezoid. The -2 just carries along from before. And so now this is the first approximation that we have introduced into the method of characteristics. And so here it is again, all laid out. Now I know I'm moving fast and I don't expect you to be able to take notes on this. Again, I would encourage you to buy the textbook, and there are other good textbooks as well. Okay, so before we move on, I want to note that, yeah, right now, this is an second order accurate scheme, typically denoted as order of delta x squared. And we'll talk a little bit about that at the end of this video and more in the next one, as it does relate how your error terms change with a change in grid spacing. And big picture, yeah, typically a second order scheme is going to be more accurate than a first order scheme. That's based on the assumption that the error is small. The square of a small number is even smaller, but then again, there's always a risk that your error is larger than 1, and then, well, you've made it worse. Okay, so here's the boxed equation. This is all brought together. This is the integrated equation, second order accurate, that's valid along the C+ characteristic. A lot of work to get there, but hopefully you're not hitting the I believe button. And just to be clear, in parentheses is the quantity xi minus xi minus 1. That's just going to be our grid spacing in the x direction, delta x. Okay, so now we can do the same thing along the negative characteristic. It's the exact same procedures, exact same amount of work. And I'm going to skip all that and just give you the boxed equation. There are some noted differences. We have some negative signs that did not appear along the C+ characteristic, so they are different. But taking a look back at that, these are the two equations. We see that we have two equations, two unknowns. Anything at the j+1 level is an unknown. So we have head and flow, two unknowns, two equations. We can solve that. So algebraically, that's what we do. Okay, to simplify things is that we take the quantity A over GA. If you remember my video from the Joukowsky relation, this falls out from that. Oftentimes it's referred to as the elastic factor because it does take into the compressibility of the liquid and elasticity of the pipe. And so we're going to substitute capital B for that. And this grouping for the frictional loss, the head loss in the pipe, we're going to call that R. And when you do that, then the head loss is equal to R, the resistance times volumetric flow rate squared. Okay, so when we make those simplifications, it gets a little bit cleaner, but we still got some algebra to do. Okay, again, so I'm going to be going through this fairly quickly and doing some simplifications and some groupings. I come up with these equations, which right now makes no sense, but they will in a second, and then I define the positive characteristic equation CP and BP as below, and for along the negative characteristics CM and BM. Okay, so once I do that, I can solve for my two unknowns, head and flow, at the point I, j+1. A lot of algebra went through there straight out of the textbook. That's the purpose of this video. And I'm going to box those equations because we are going to be using those extensively. Okay, so again, let's return to our pipeline, and eventually we are going to analyze this with an instantaneous closure of this valve at the end. That's the flow is going to atmosphere outside this valve, one of the simpler situations that we can have. Note that we are going to have inline segments, and we need grid points from 1 to n+1 to accomplish that. So grid point n+1 is at the inlet of the valve. Okay, so let's overlay our grid, and in green you'll see our positive characteristics, and in gold we'll see our negative characteristics. It's getting kind of messy because we got a lot of intersections there, so I'm not sure this cleans it up. It hopefully makes it a little bit more understandable. And that anything in a circle is a calculation point, and it's an interior point. Anything in a square along the left-hand side, well, that's the left boundary condition. And the right-hand side squares is the right boundary condition. And you'll notice on the left boundary condition, we're going up. We have to march up in time, is that you only have the characteristics that are flowing in the -x direction or the C- characteristic. So we have one equation, two unknowns. So our boundary condition is going to supply us with the other equation for that. Similar story on the right boundary. We only have the characteristics flowing To the right, the C plus characteristics, we have one equation, two unknowns. Again, we need to introduce another equation, in this case for the valve, that's going to give us the second equation necessary for a solution. Okay, so let's start with the interior nodes, and we've already done all that work actually. That's nodes 2 through n, so they're not at the boundary condition. And so at time is equal to 0, we have the initial conditions. We're going to need that. And so we know all the information. And now for nodes for 2 for n, we have everything we need to calculate those. And we're going to march up in time doing the interior nodes. And we've already got those equations. So those equations, along with these complementary equations out here on the right, that's everything we need to calculate the interior nodes. So we can march up time with the interior nodes at that, but we still need the left-hand boundary, or node 1. Now that's a reservoir, so that's equal to the fixed grade in that large reservoir. And again, the only characteristic that applies, because we still need to find the flow, and this equation doesn't give us flow, so we're going to be using the C minus characteristic. And repeating that here, this is our unknown, but the left-hand side is our fixed grade node, so we have everything we need. Just rewriting things to notate that this is all being done at node 1, and for the left characteristics starting at node 2. And we can solve for the flow at node 1, and once we know that, well, we already know the head there. Okay, so now let's start at node n plus 1, which is the inlet to the valve. And again, we have one characteristic, the C plus characteristic, so let's write that for node n plus 1, so that's one of our unknowns, and so we have two unknowns, one equation. And again, writing the complementary equations, denoting the right characteristic going from node n to node n plus 1. And now we introduce an equation for the valve, the head loss across the valve. There are many different ways to express this, but we're going to define a resistance of the valve times the flow squared. So this will be a function of the minor loss. The resistance of the valve will be a function of the minor loss coefficient. Could be if you're treating it like an orifice. There's an orifice equation that you can use. But anyway, you need to separately calculate the resistance of the valve, and that gives us the second equation with the introducing the second unknown. So now we have two equations, two unknowns. When you substitute this equation in, you get a quadratic, and so this would be the solution. And once you know the flow, you can go back to the C plus characteristic equation, solve for the head, or you could just use the head loss equation for the valve. So now we are able to calculate the head and flow at each point and march our way up the grid. Now, one thing you notice is that there's a large number of points, and that is one of the big disadvantages of the method of characteristics, is that it's a calculation intensive. But the authors came up with a pretty clever scheme to help minimize that. And you'll notice that if at time is equal to 0, everything is known. That's our initial condition. So everything is known at time is equal to 0. And at the first time step, we choose to only calculate the even nodes, as denoted by the circles which I'm marking out here. Okay, so we don't need to calculate the ones on the intersections at the odd points, because as I march to the next time step, I'm only going to be calculating the odd nodes. And so roughly, you've cut your number of calculations by half. So that's a good thing, because method of characteristics is very calculation intensive, and this is sometimes referred to as a staggered grid. Now the question is, does that impact the accuracy? Well, it really should not, because the information at any of these points only depends upon, you know, the characteristics that are running into it, and we've not violated any of that. We're still, in all of our calculations, we're using a Courant number is equal to 1, so we should maintain our accuracy. But we're going to be investigating that. This video has already gone long enough, and what we're going to be doing in the next video is a grid convergence test. Anytime you're using a finite difference or other scheme, we should be doing a grid convergence test. What does that do is that, well, let's just check our theoretical convergence. We expect it to convert, be a second order convergence. Do we obtain that? Well, if I was solving an elliptical equation, say steady state two-dimensional heat transfer, yeah, I'd expect my grid convergence to be, I could take it up, you get pretty darn close to 2, 1.98, even 1.99. Again, we're throwing out the higher order terms, so you're probably never going to really get 2. But how we're going to do that is basically this is a Taylor's expansion, and we're going to throw out the higher order terms, and then we're going to do the calculations using, in this case, 4 different grids, and set this equation up for each of the 4 different grids, and it's going to allow us to calculate the actual or observed convergence. Is it going to be a 2? No, likely it's going to be less than 2. How much less? Well, we'll get into that. There are other things that can impact it. Maybe the boundary conditions aren't really second order accurate. So that's the type of investigations that we're going to be doing in the upcoming video. So I know this video went fast and lots of equations, but I hope it gave you an understanding of the how method of characteristics is set up for waterhammer analysis. And we're going to be using that as our starting point for some upcoming videos. So I hope you found it useful. Please like and subscribe. But more importantly, have a great day.